Aloha and welcome to this screencast on automated quality assurance. You know, this could be really, in some ways, the most important module of the entire semester for you. And I say this because quality assurance is a very, very important, if not a central aspect of software engineering. And the presence of tool support for quality assurance can radically change your whole notion of how to do development, your whole notion about how to do testing, reviews, and so forth. It impacts everything. Finally, the kinds of quality assurance tools that are being developed for Java in particular are really amazing. And I think you're going to find it really, really interesting to get familiar with the tools for quality assurance that we'll be using in this course. In many ways, I don't know of any other language actually that has as good a set of quality assurance tools as the Java tool ecosystem has. So that's one nice thing about Java. Okay, so let's get started. The objectives for this module is to understand exactly why we want to have automated quality assurance and how it's performed, and what the alternatives to automated quality assurance are, and we're going to call them manual quality assurance for this course. We're going to learn about a few different tools, and we're going to learn about the specific strengths and weaknesses, pros and cons, synergies and so forth between the three selected quality assurance tools we're going to be using for this course. So when I talk about quality assurance, what the heck do I mean? Well, at the highest level, what I mean is how do we satisfy the three prime directives? That's the overarching issue of this course, is the three prime directives. Can a user find some useful functionality? Can an installer be able to actually put it on a system and maintain it over time? And can a new developer, jump in and make extensions to the software system, relatively easily? So that's a very high level, but those things aren't real operational, okay? And so it's nice to have a set of low-level things that are easier to check for, that we could almost have a checklist for. And so that's what we're striving for, is a set of low-level guidelines that we can implement and put into our software development procedures that don't guarantee that we'll satisfy the three prime directives, but are going to help us get there, okay? So at the low level, there are things like having quote-unquote good tests, and we'll find out more about what that is later. Conforming to coding standards so that the code all looks like it was developed by one person, even if multiple people were involved. And looking for certain kinds of code smells or heuristics which indicate that there might be problems. And finally, just overall general conformance to requirements. The way we're going to do this is do quality assurance in general is through basically two kinds of things: manual quality assurance and automated quality assurance. So when I talk about manual quality assurance, what I'm basically talking about are two things. One is testing and the other is code review. Okay? And manual quality assurance is essential. Okay? You got to do it if you want your system to be of any reasonable quality. And the strengths of doing manual quality assurance is, first, that it's very easy. Well, it's not very easy. It's straightforward with manual quality assurance to do things like check that the requirements are being satisfied. Okay? You do a code review. You have a checklist that shows the requirements. You ask a variety of people if the requirements are being satisfied. You have a very good chance of uncovering, things that were forgotten during the implementation of the system. And in general, with manual quality assurance, the false positive rate is quite low. What that means is that when manual quality assurance raises an issue, that's quite likely to be a real issue that bears investigation and changes. The problem with manual quality assurance is that it's, first of all, extremely expensive for assessing certain kinds of very low-level issues like, two-space indentation. Okay, you don't want people reading the code just to see, or a checklist that says read all 100,000 lines of code to check to see if any lines didn't obey two-space indentation. That would be crazy. Okay, the second thing is that it's just quite expensive. And it's expensive in terms of the human overhead of writing the test, performing the code review, but then also in an evolutionary context, here's the issue. you do a review of a large system. It's all been reviewed. You believe it's good. Then you go in and you do development for 2 weeks. Okay? Well, now the question is, do you need to do another review? If so, what do you review? Do you review just the lines of code that were changed? Do you need to review a much bigger piece of the system because there could be ripple effects? You know, so the problem with this manual quality assurance is that it's expensive, okay? It needs to be done. There are certain kinds of things you can't find without it, but it just is a costly kind of quality assurance to do. On the other hand, we have automated quality assurance, and that basically means that you're going to apply a tool, potentially configured through some kind of configuration file, to your code, and it's going to look for classes of general implementation defects, okay? And unlike manual quality assurance, which is, you know, kind of has to be developed uniquely for each project. So the set of unit tests that you apply to one project usually can't be applied straightforwardly to a different project. You got to make different unit tests because another project is another project. It can't just use the test cases from your old project. On the other hand, with something like Find Bugs or PMD, you can take the set of tests that you check for on one project and just run it over a new project. And it's totally good. It'll find those kinds of problems that you're interested in on all of your projects without any change. So the strengths of it is that on one level, it's much, much more economical. It takes, you have to learn the tool, you have to configure it once, and maybe do a little bit of configuration for a new project. But in general, as that project is evolving over time and you're adding new code, subtracting code, doing things to it, basically at the flip of a switch, you can run your quality assurance over it, discover new defects, and the incremental cost is zero. Once you've got it configured, it's almost cost-free to run that thing as multiple times every day, every time you build the system, whatever you want, okay? Which is completely unlike manual quality assurance. The weaknesses are totally complementary, okay? The weaknesses are it has the potential to have a high false positive rate. So these quality assurance tools are not, their issue is that they can often flag quote unquote problems with your code that when you actually look at that line of code, you go, no, that's okay. I very deliberately did it that way, and even though you think this might indicate an error, no. In this particular case, this is the right trade-off between various things. So you can have these false positives. The tool thinks it's an error, and in fact, it's not, as far as you, the developer, are concerned. The second thing is that these quality assurance techniques can't tie into the actual specific requirements for your software system because they're just not that smart. Okay, they look for general violations of general coding constructs or idioms for a particular language. Okay, whoops. So you put these two things together, manual and automated quality assurance, and you've got a very powerful suite of techniques that you can apply to raise the quality of your system. And that's what we're going to try to explore in the remainder of this course. So let's look at some of the tools that have been out there. The first tool, the granddaddy of them all, was lint, developed originally for C. That's because C had all sorts of ways that you could mysteriously screw up and not have your program work correctly due to the language being, about 3 inches above assembly language with respect to abstraction level. It's one of its strengths, actually, because it's very close to assembly language, but one of its weaknesses is it gives you a lot of rope to hang yourself with. So lint was developed to provide a kind of a post-processor over your code, or a processor over your code that would look for certain kinds of things that tended to indicate errors. Here's an example of some output looking for deallocation of memory that's inappropriate, or use of pointers in weird ways. So lint was a tremendously useful automated quality assurance tools for the C folks. Another kind of tool is called FXCOP. This is of interest, probably well known to any of you that do .NET development. The idea being that there's a lot of kind of idioms and things, standards you need to conform to for developing .NET applications that aren't really embodied in any particular tool or the language itself. So FXCOP is this kind of plug-in that looks for those kinds of violations. Here's an example of the kind of the issues with assemblies, issues with identifiers and so forth. So FXCOP is kind of like a I'm not super familiar with it, but it looks to me to be kind of like the .NET version of kind of a combination of find bugs and PMD. Okay. There's a company called Coverity that is doing automated quality assurance on open source projects to kind of raise public awareness of the level of quality of the open source projects that are being used, across the internet, and to kind of spur the community on to address some of the security and other kinds of problems that might be present in these open source systems. So you can look at that company. It's very interesting to read some of their reports. You can see here some of the kinds of things that they look for: null pointers, resource leaks, buffer overruns, etc. Some of these being very kind of buffer overruns in particular can be major sources of security problems. The percentage of the open source projects that they found that had one or more of these issues in them. Moving into the Java world, there's a system called JDepend, which basically analyzes your software system and creates a report that shows the dependencies amongst the various classes and packages in your system. And basically that means how many clients are using a particular a class or package. Okay, that's your afferent couplings, and then your efferent couplings are the number for any given class, how many other packages it's happening to be using. Okay, and so this ingoing and outgoing dependencies, the more of these things that you have, okay, the more complicated your software is, the more that changes to one place in your system can affect other places in your system. Okay, and so in a sense, the more brittle it is. So looking at the dependencies, incoming and outgoing in your system, can provide a sense for the complexity of your system on a high level, and thus how prone it might be to errors as it's maintained over time. You can also have cycles, right, where A depends on B, depends on C, depends on D, depends on A again. Okay, and cycles can create, lots of makes it much harder to maintain the quality of your system over time, because the kinds of implicit problems that can occur there. Structure 101 is another system that that's pretty cool. It provides this metric that enables you to understand both the complexity, not only with dependency, but other kinds of factors they bring in as well. The complexity within a method in terms of the amount of loops and conditionals within it, as well as the dependencies, incoming and outgoing dependencies between classes, and they gather that together to create this kind of composite metric, which enables you to understand whether a system is structured in a way that is prone to error or not over time. So useful for larger scale systems. Here's a little chart that shows some of the stuff that they look for, and then they can also track over time by looking at your source code repository, whether complexity is going up or down. Here's this XS metric, which they combined, the complexity inside a class with the dependencies between classes to get this kind of composite metric. It's pretty cool. Here's a more lighthearted attempt, crap for J. These folks, some of the Agile guys got together. They said, listen, there's kind of two things we're worried about. We're worried about the complexity of a particular class. Okay, if a class is more complicated, it's more prone to errors. And then also we know that if a class isn't tested, then it's more prone to errors. So let's put those two things together, and we'll say that if a class is complicated and not tested, it's crappy. Okay, and it's pretty easy, with tools to kind of test for the internal complexity of a class and test for whether it's getting covered by tests, and we can create this metric of crappiness. And then they just went to town with all the kind of cute little word puns on this. But in essence, it's kind of an interesting approach to thinking about your code in terms of identifying places in your system where you might want to focus your efforts, either to reduce the complexity of your classes or increase the coverage, the testing of these classes, in order to kind of compensate for its innate complexity if it has it. So here's a crap report. And and you can see it's looking at the complexity of the system, the class, the coverage of it, and then it produces this crap metric from it. Okay, so that's an overview of some of the tools that are out there. Let's look at the ones that we're going to be using in this class. First is CheckStyle. There's a little screenshot. And the idea of CheckStyle, we're going to do source code analysis. Okay, it started out just looking for kind of formatting level issues in your code. Now it's got some design level stuff going on. It's got these classes of checks, Java docs, naming conventions, white space, blah, blah, blah. You can add new checks, or you can configure the current checks, and then you'll see when we run CheckStyle in the class, there's this checkstyle.config.xml file that's downloaded that provides a set of checks and customizations of those checks to have CheckStyle enforce our coding standards that I've set up for this class. Okay, and here's an example of the output where CheckStyle has been run over some code and it's found some errors. Pretty straightforward. PMD is another kind of source code level analysis, and it started out life much more as kind of a complement to CheckStyle, looking at more design level stuff. Now those two tools are kind of merging, and there's a lot of overlap between them, but there's still in some sense there could be some kind of merger where you'd only need one, but for the time being there's enough different stuff that each of them tests that the other doesn't, that it's useful to use both of them. And so here's an example of a report for PMD. Okay. All right, then find bugs. So CheckStyle and PMD are rather similar. They're source code level analysis, focusing both on the low-level stuff, kind of formatting level stuff, as well as some design stuff. Find bugs is a horse of a different color because it focuses on bytecodes, not source code. And because of that, it can find certain kinds of errors that other the source code analyzers can't, because it can actually do data flow analysis back and forth. So here's an example where you have a string B, you set it to be Bob, and then you call the replace method on the string B to replace all occurrences of B with P, which creates a string called pop. Okay? Now the problem here is that we're not actually, when we call this b.replace method, we're not actually destructively modifying the variable b. Okay, we're returning a new string. So that middle line of code, b.replace p with b, it basically creates a new string, and then that new string is immediately thrown away. It's not assigned to anything. Okay, so find bugs can actually look at that line of code and go, wait a second, you've just done something in the language which it doesn't make any sense that you've just done this, because there's no way for the it doesn't have any side effects, the replace method, so there's no way in your program that you can benefit from the results of that computation. Okay, so find bugs can flag that, whereas CheckStyle and PMD they aren't able to detect those kinds of errors because they're not actually able to understand the flow of data and control through the program the way that find bugs does. Okay, so here's the kinds of output that you can get from the find bugs analysis. It could do things like exposing the internal representation and lots of neat things that you can't get from source code analysis. Find bugs has found plenty of errors in my code, and I think you'll be fascinated when you start to look at the find bugs errors, because you'll go, wow, I didn't really know this about Java until find bugs pointed out that this was a potential problem. Okay, so as I said before, the reason why we're doing this stuff is to provide you with different kinds of techniques to build high quality systems as fast as possible. Okay, and efficiency and productivity is a huge concern of mine in this class. I'm trying to give you hints to have you study effectively, to have you assimilate the material effectively, which means assimilating it fast. And as I say, sometimes what I've talked about before, that means actually taking notes while you're watching these screencasts, because even though that will require the screencast to take you a little bit longer to get through, you'll have invested time in assimilating the material, which will lead to a payoff later on, because you'll have actually learned this stuff and you won't have to review this as much, or you'll be able to pick up other stuff faster. Okay? So similarly with software development, I'm trying to give you techniques which enable you to write high quality code as fast as you possibly can. Okay? And so this combination of automated and manual quality assurance is one of these, places where what I'm hoping for you to learn over time is what kinds of things can automated quality assurance, CheckStyle, FindBooks, PMD, what kinds of errors can those systems detect? Okay? So I don't look for those things in my reviews or in my unit tests. Okay? And that's really great. That means that I can focus my unit tests, focus my reviews on stuff that doesn't concern the kinds of issues that my automated quality assurance tools can find. And then of course you want to integrate automated quality assurance into kind of your daily development process so that the code is always free of those defects and it never even rises to the point of an issue, okay, when doing your manual quality assurance techniques. All right, thanks a lot, and talk to you soon.